This is a webinar presenting the rationale behind some of the choices IMR has made for how we are mapping mesopelagic resources under the MEESO program. The viewpoints presented do not necessarily represent a general consensus in the MEESO program, but is more an explanation as to why IMR in the MEESO program has opted to move away from the reliance on hull-mounted acoustics when it comes to quantifying mesopelagic resources. But to start things off, let's give some credit where credit is due. The use of hull-mounted acoustics has some very desirable characteristics when it comes to scanning the mesopelagic. It is by far the most time-efficient way of scanning large volumes that we currently have. It is presently widely available. We've got data available for relatively long periods of time, and it can be relatively cheaply deployed on ships of opportunity, etc. In principle, the common method employed is very simple. A vessel traverses an area, measuring all acoustic backscatter returned from the water column underneath the vessel. The first step of converting the sum of this backscatter to variables of ecological interest is to divide by the average sound backscattered by an individual. If we have a good estimate of this quantity, we would end up with an estimate of the total abundance of individuals observed with the echosounder. This quantity can again be converted to an estimate of total biomass in a second step, if we have a good estimate of the average weight of individuals. Of course, this is a very simplistic explanation of the procedure, but the main problems should already be evident. The quality of our ecologically relevant estimates depend on the quality of our estimate of average backscatter per individual, as well as average weight per individual. There are other issues as well, such as how to partition the acoustic backscatter when multiple components are present, etc., as well as uncertainties introduced by various aspects of the acoustic method. But the main issue we perceive at the moment is that the ecological output is critically dependent on the supporting data, most specifically the catches, which is why IMR has dedicated a lot of resources to developing and testing troll equipment and methods in order to increase the quality of these data. But that is another presentation. But just to make it clear, we have not abandoned acoustical methods altogether when it comes to mapping the mesopelagic. We just use the available instruments differently. Throughout the MEESO project, we have relied on using acoustic instruments submerged down to mesopelagic depths, perhaps best exemplified by our towed body named MESO, which you can see some pictures of here on this slide. This is a platform where we deploy a number of instruments, but most importantly in this context is the multiple broadband units and transducers. In the picture on the left you can see a 333 kHz transducer looking forward from the front of MESO. The other 4 transducers are directed downwards. So, what do we gain by lowering the acoustic instruments down to mesopelagic depths? In short, the most important reason for us to do this was that we can then resolve individual echoes at these depths. The echogram on this slide shows an example of typical output from the MESO echo sounders at mesopelagic depths during a deployment. Each of the marks shown on the echogram represents the echoes given off by a single organism as it passes through the acoustic beam underneath MESO. As you see, we are usually able to separate individuals, and we also tend to get multiple echoes from each of them. Since we know the volume of the acoustic beam, it is trivial to convert these echo registrations to organismal densities. Thus, we're able to arrive at the same estimate as that obtained in step 1 of the hull-mounted procedure, with other and far less uncertain assumptions than those required by the integration method. And yes, for those of you that wonder, we are looking into avoidance of the MESO platform itself, but I won't go into details of that here. Now, I'll just point out that the acoustic equipment on MESO are split beam transducers, so it's capable of directly measuring the acoustical backscattering per individual. So we can use those data to actually provide the average signal strength needed to perform step 1 in the hull-mounted procedure, which in itself takes out a large source of uncertainty in the conversion of backscatter to densities. The heat map presented on this slide is based on MEESO data at 38 kHz from a single deployment, and it shows the densities of detected organisms as a function of depth and signal strength, the target strength of the echoes. It is immediately evident that there are patterns in this heat map, which may also be used to separate different acoustic categories. In this case, the 38 kHz data was not broadband, which means that for each echo we only have a single estimate of signal strength at the central frequency. However, we have several different transducers available on MEESO and deployed several of these in broadband mode, meaning that the output we get is actually a spectrum of signal strengths over a frequency band. So in this work I'm presenting here, we used broadband data from the 70 kHz transducer to see if we could identify different groups of scatterers and gain knowledge on their behavior and distribution from these data. So these are published data from a 2019 cruise going from Cape Verde up to the English Channel. You can see the cruise track along with MEESO stations on the map in the center. The echograms on the left show the hull-mounted results along this cruise track, 18 kHz data above and 38 kHz data below. And you can sort of see one of the issues with using hull-mounted data for mapping straight off the bat, as it is fairly obvious that the pattern you see depends on the frequency you use to make the observations, which to me is slightly disconcerting if you want to use the data to come up with a resource map. Anyway, using the information in the signal spectra from the individual echoes resolved with the submerged echo sounders, we used a clustering procedure to group the echoes into coarse acoustical categories and looked at how the vertical abundance distribution of these categories varied over the transect we covered. The right-hand figure shows the average spectra of these different clusters, and we identified some patterns over the transect in terms of their abundance and vertical distribution. Details of these results can be found in the Agerstedt et al. Publication. But this work highlights that resolved echoes can be used to tentatively identify components and also geographical patterns in abundance of these components. As you saw on the last slide, the results you get with acoustical methods depends also on the frequency you use to obtain the results. In general, higher frequencies are capable of mapping smaller organisms, but higher frequencies also have higher attenuation losses, meaning that high-frequency hull-mounted echo sounders cannot cover the entire mesopelagic zone. Of course, with submerged acoustics, you can get data from high-frequency echo sounders also at mesopelagic depths, which may be better for mapping smaller components, such as, for instance, euphosids. The graphs shown here shows a comparison of vertical density profiles obtained with two different frequencies at the same station, documenting much higher densities of small or weak scatterers at depth in the high frequency data than in the low frequency data. This means that we have the opportunity to observe more mesopelagic components the more frequencies we add, meaning we get a fuller picture of what is actually there. It may also mean that we get a chance to observe the distribution of both predator and prey components, enabling ecological studies. Now, you cannot really touch mesopelagic acoustic studies without mentioning resonance effects for gas inclusions. I'll just start by saying that resonance effects don't really affect the results obtained by direct echo counting methods, but they may be a serious source of bias if you use echo integration, as one normally does for hull-mounted data. So, in most cases, resonance is treated as a nuisance factor, and there is a certain amount of hand-waving going on in the scientific community, where the possibility of resonance effects are invoked to strike down the use of any acoustic method to estimate mesopelagic resources. A typical example of this would be the claim that biomass estimates are wrong because there could possibly have been resonant siphonophores present, even without any evidence of the presence of siphonophores. Don't get me wrong, I'm extremely skeptical of the use of hull-mounted methods for mesopelagic resource quantification, but the support for the general importance of siphonophores in mesopelagic backscattering levels is apocryphal. While there are a couple of studies that have documented strong local effects under very particular circumstances, a general scientific basis for the importance of siphonophores for mesopelagic scattering is lacking. Anyway, while resonance effects may be a nuisance in converting integrated backscatter to abundance or biomass, it also presents some possibilities. Since it is so important, the phenomenon has received a lot of focus up through the years, though in the case of resonance of mesopelagic fishes, a lot of the parameterizations currently in use are quite dated. In our case, the nice thing is that resonance presents a scattering phenomenon that we have a physical model for. In this case, meaning we can combine measurements and models to derive knowledge about the properties of the organisms, the acoustical properties. And so one of our very talented acousticians set about combining theoretical models with our in situ broadband measurements to improve our knowledge about the acoustical properties of mesopelagic fishes. Details of models and methods can be found in his papers, but basically broadband spectra were fed into models and the physical properties of the individual scatterers were obtained through optimization, i.e. model inversion based on the real data. The figure shown on this slide shows the steps of this procedure in some detail, starting with isolating the individual echoes, extracting the broadband spectra, and then the iterative fitting of models to data, delivering parameter estimates. 3 publications based on this work are listed at the bottom of the slide. The parameters obtained can then be reused in predictive models of organism target strengths, thus reducing the uncertainties inherent in step 1 of the integration method, especially when limited measurements or catches are available. The method can, however, be taken even further. One of the organismal parameters that can be estimated is the size of the air inclusion, in this case the swim bladder for fishes. If one assumes that the mesopelagic fishes are neutrally buoyant, and make some assumptions about the density of the flesh of the fish itself, one can arrive at a direct estimate of fish biomass. This work was spearheaded by 2 of our very talented postdocs, and the method provides a completely catch-free approach to biomass estimation. All of the other methods I mentioned so far require some sort of size distribution based on catches or pure assumptions, whereas this method requires both resolved echoes and some assumptions about the physical properties of the organisms. But these assumptions are basically completely different from those required for the other methods, so the method may be used to come up with a completely independent estimate of biomass, albeit only for fishes with swim bladders. So, I'm back with the heading I started with. As should be clear by now, converting mesopelagic backscatter measured with hull-mounted echo sounders into abundance and especially biomass levels of mesopelagic organisms is fraught with difficulties. And as a general rule, I don't think it currently can be used to provide accurate estimates. I say in general, because there are mesopelagic components where we are both capable of identifying these components and also have decent acoustical models and can also obtain decent size distributions, so that the acoustical method is feasible. The genus Mauriolicus comes to mind, and blue whiting is in effect a mesopelagic species that is already monitored acoustically. However, for most mesopelagic resources, accurate mapping by the classic acoustic troll method is a bit of a pipe dream at the moment. However, using the results of submerged acoustics, either alone or in combination with hull-mounted acoustics, I think reasonably accurate abundance mapping is possible, though the conversion of abundance to biomass levels require highly specialized troll equipment, which is the subject of another one of my webinars.